Okay, so good morning, everyone. I am Gracecoccagna, currently a recent graduate of Dickinson College, where I majored in data analytics and math, and now I'm serving as an MLB Statcast data analytics intern. And today I would love to share with you my exciting research on one of baseball's most subtle yet powerful weapons, and that is pitch tunneling. So we're going to explore how we can use data to measure and evaluate pitchers' art of deception. And through this analysis, we can uncover how tunneling impacts the critical battle between pitchers and hitters. So let's dive in. To start, let's go over a roadmap of what I'll be sharing with you today. First, ideally, I'm going to be defining what pitch tunneling is, and then go into some of the criteria and characteristics of an effective tunnel. Following that, we can start putting numbers to things and quantifying tunnel effectiveness and how that can affect the width rate and run value. And then we can get into the fun part, looking at the league leaders right now in different tunneling metrics, and then end off with some future considerations and next steps. So to begin, what is pitch tunneling? And ideally, pitch tunneling is when there are multiple pitches that have a very similar trajectory and flight path and then diverge at the last minute. So ideally, this is a technique that pitchers can use to try and trick or deceive batters. Ideally, the result in this is less reaction time and therefore more whiffs and or a weaker contact. Here is a good video clip describing what pitch tunneling can visually look like. So we can see two consecutive pitches, and when they're lined up next to each other, you can see that they are diverging at that last minute, tricking the batter. So to jump in on my methodology, obviously there are a lot of moving parts and things to consider when doing this tunneling analysis. So I needed to break it down a little simpler. Ideally, I'm looking at two consecutive pitches and where those pitch types are not the same. So we're looking at consecutive combinations that could be maybe a fastball and a curveball or a sweeper and a cutter. And ideally, we want those two pitches to be passing through what I'm going to classify and reference as the triple tunnel. And ideally, the triple tunnel is something that pitches need to go through in order to be considered tunneled, and that is the 3 points are the gate, the recognition point, and the commit point. So starting with the gate is closest to the pitcher, that is going to be the entrance to the tunnel. The recognition point is a little bit after that, but that's when the pitcher or the batter, I'm sorry, can recognize what that pitch is. And then lastly, the commit point, which is where that batter is going to decide, am I going to swing at this pitch or hold back? And ideally, if two consecutive pitches can cross through a threshold between these 3 points, we can then use the separation point, which is after the commit point and before the plate, to tell how far those two pitches diverged from each other. Here's a good visual to describe where these points are in the flight path. So here's an example of two tunneled pitches, a fastball and a slider, but you can see that the gate is very close to the beginning of the flight path, followed by the recognition and then the commit point. So diving into the commit point and the methodology behind that. So the commit point is going to be the closest point to the batter. So working backwards from the batter to the pitcher. That commit point is when that batter is seeing that pitch and deciding this is my pitch and I'm going to knock it out of the park, or I'm going to hold back and take this one. So after the commit point, if a batter has decided that he is going to swing at that pitch, it's often very difficult for him to pull back from that decision. And the commit point, which I had confirmed later on, but the commit point is 233 milliseconds since the pitcher release, or 167 milliseconds since the plate that our wonderful Tom Tango has came up with. So ideally, my first step was to confirm this commit point. And as we can see here with 4 different swing paths of biomechanical data, we're looking at right-handed batters and their elbow. So we have a check swing, a home run swing, a late swing, and an early swing. And ideally, we're looking for that change in movement, that change in direction. So where the slope is changing. So on that left-hand side, we can see a pretty consistent dip between those 4 swings at around 150 to 175 milliseconds since plate, which thus confirms our 160 seconds for the commit point. Now that we have established where that commit point is, we want to figure out what threshold that may need to be at the commit point. So one metric that I used for my analysis was the XZ distance, and that is ideally taking the Euclidean distance or the vertical and horizontal averages between the pitch coordinates of these 2 pitches at the commit point. So here you can see that we have a very bell-shaped curve here, but the parameters that I will note on this is we're looking at a first pitch strike in the heart of the plate, followed by a second pitch strike, and those 2 pitch types are not the same. So we can see we're going to be looking at around 4 to 7 inches for that threshold would be a good reference point, ideally, to look at. Looking at another metric, which is whiff rate, which is ideally just a swing and a miss on that second pitch with the same parameters, the same, except we're looking at whiffs instead of weak contact or foul balls. That would be included as a strike. But this graph is a little more helpful because we can see the downward trend in that whiff rate, looking as the thresholds increase. So ideally, this could hint to me where we want that threshold to be. And to my opinion, I think that the threshold for the commit point should be sitting at around 5 inches. So now that we have established that, we're diving into the recognition point. So this is that second point in the triple tunnel, moving a little further away from the batter. So the recognition point, like I touched on before, is when the batter can identify what type of pitch is coming at them, what that trajectory looks like. Ideally, they can figure out if it's a fastball or a curveball. They're looking at the spin and movement of the ball coming out of the pitcher's hand. And from Tom Tango's analysis before, this is sitting at 100 milliseconds since the release. Here's a very similar graph to the one that we just looked at with the commit point, but again, we're looking at that XZ distance, which is the horizontal and vertical average of those 2 pitch coordinates. And we can kind of use this to eyeball where we may want that threshold to be. And to my understanding, we're looking at around 3, 4, 5 inches would be a good reference point. And ideally, we're going to want that recognition point threshold to be smaller than the commit point since we're moving backwards. So if we establish around 5 inches for the commit point, then the recognition point would sit around 4. And further confirming that and helping to identify where we want that threshold to be, we can look at the average run value by the distance of the threshold at the recognition point. So ideally, the run value is, does this pitch help or hurt the pitcher? It's the estimated number of runs a pitcher is preventing or allowing. So in a pitcher's perspective, we want this value to be the most negative. So you can see at around 9, 10 inches of a threshold for the run value becomes positive, which is bad. We don't want that for the pitchers. So we can lean more towards the smaller threshold side with the higher negative values. So this again can help support that 4-inch threshold for the recognition point. And now the last part of that triple tunnel, the third part, is that tunnel gate. And this is going to be as close as we can get to the pitcher. So ideally, the tunnel gate is that entrance into the tunnel. And this was a point that I had created for this triple tunnel. And batters are typically looking at the release angle. They're looking at the shoulder and wrist when a pitcher is pitching. And to identify that ideal distance for that gate, I analyzed the release, which was 0 milliseconds, and then 25 and 50 milliseconds since release to figure out what that ideal distance would be for the tunnel gate. Looking at run value again for these 3 points, we have 0, 25, and 50 milliseconds since the release. And I'm not seeing too much of a fluctuation between these 3 points. So to me, this is suggesting that we are going to go ahead with 50 milliseconds because it's consistent with an even distance where it's not super early straight from the hand, but there's still some wiggle room before the ball is entering that tunnel. And then now establish where that tunnel gate is sitting at 50 milliseconds. We can do an analysis to look at the run values for different tunnel gate thresholds. So the greatest or most negative run value is sitting at around 0 to 2.99 inches, and that is consistent with the 4 and 5-inch thresholds, with 3 being the smallest. So it's pretty clear that we can identify what that threshold is at the tunnel gate. So now looking at putting all of this together, we have identified our 3 checkpoints and what that threshold to be in order for these pitches to go through that triple tunnel threshold. So we have the tunnel gate, which is less than or equal to 3 inches, followed by the recognition point, which is less than or equal to 4 inches. And then lastly, we have the commit point, which is less than or equal to 5 inches. And a pitch is considered to be tunneled only if it stays within all 3 of these thresholds simultaneously. Now that we have established where the tunnel is, we can start looking at how far these pitches diverged from each other at the separation point. So the separation point is after the commit point, but before the ball crosses the plate. And a reason we don't want to look at the pitch coordinates of the ball when it has already crossed the plate is due to catcher framing and a lot of movement there, which can cause issues with our analysis. So ideally, we can use this point to identify how far these 2 pitches diverged from each other. And this occurs at 300 milliseconds after release. So that's giving us enough time after the commit point to allow those 2 pitches to diverge from each other. Ideally, a greater separation distance at the separation point, when of course paired with a more negative run value and increased whiff rate, would signal a more effective tunnel deception. Looking at a similar graph from earlier in the presentation, we can now add that separation point onto the 2 tunneled pitches trajectories. And this is just giving us a visual of where that is in reference to those other 3 points in the tunnel. Now that we have identified all of that, we can begin putting numbers onto all of this and start quantifying pitch tunneling. To begin, the first metric that I created was the tunnel strike rate. So the tunneled strike rate is calculated by the number of strikes on a second pitch from tunneled combinations divided by all total qualified tunneled combinations. This is an important metric because it really measures consistency and success when a pitcher is tunneling. So ideally, how often when they tunnel does that lead to a second pitch strike, thus tricking, fooling, deceiving the batters as they thought possibly another pitch was coming at them and it diverged last minute. The next metric that we can look at is the average tunnel distance. So this is the final distance in inches between the 2 pitches at the separation point. So ideally, we're looking at how far apart these 2 trajectories went and how far away the 2 pitches were. Ideally, a larger average tunnel distance means that the pitches end up farther apart from each other at the separation point. Following that, two more metrics that we can look at are very similar. However, we're looking at the second pitch of tunneled sequences, looking at the run value and the width rate. So the run value is important because it can measure the real game impact of tunneling. For example, fewer runs scored or more strikeouts. And this is more accurate to look at different outcomes that aren't just whiffs or barrels. Following that, we can look at the width tunnel rate, which is the second pitch width rate on tunneled pitch sequences. And ideally, the more whiffs you have, the more hitters fool, the more swings and misses you have. The more times you tricked a batter who thought one pitch was coming in that didn't end up where he thought it would be. And this is a good way to quantify the success rate of tunneled pitches. Moving on to some key insights that I pulled, I ran a Pearson coefficient test, which is looking at the relationship between two variables. So what I wanted to look at was the question if tunneling more makes you a better pitcher. If pitchers who have a higher tunnel percentage have higher whiff rate and run values. And ideally, from looking at this, I came to the conclusion that tunneling alone does not reliably increase the whiff rate. And it slightly improves the run value, but that relationship is extremely weak. So not enough data here to pull that conclusion. So ideally, just because you tunnel more, it doesn't necessarily make you a better pitcher. And now my favorite part of this project was looking at the league leaders and seeing some top 5 leaderboards and different tunneling statistics. So here are the top 5 pitchers in the league who tunnel the most often. And I think what's important to note is looking at the run values on the right side of that table. You can see that 3 out of the top 5 pitchers who tunneled the most have a positive run value, which in turn is hurtful to them. So this is further supporting that just because you tunnel more, it doesn't necessarily mean that you are a better pitcher. So looking at these examples, we can see the pitcher followed by the pitch sequence. The no order signifies that they could throw a fastball sinker or a sinker fastball. It doesn't really matter which combination or order they choose. The tunnel percentage is looking at the combinations next to that. We have, for example, on the top, there's 112 combinations. So that's how many times this pitcher has thrown that sequence. And out of that, he has only tunneled 27 of those, which comes out to about 24% for tunneling those pitches. Now looking at the tunneled width percentage on that second pitch, we can see a new leaderboard here. And we can see varying tunneling percentages here. It's important to note some constraints that I had on this table. I wanted to make sure that these pitchers had at least 100 pitch combinations and their tunneling percentage was above 5% when looking at this. But we can see the leaderboard for those who have the highest whiff rate on that second pitch. So looking at those swings and misses. Our next metric is the run value. I see a lot of familiar names on this leaderboard. I think that run value is a great metric to define the success in a pitcher, especially when it comes down to tunneling. Kevin Gossman is a very popular name, and I know that this pitch sequence is one that he uses quite often, but he has thrown this combination 518 times and he tunnels at about 10%, but he has a very good run value on this. We can also see Nathan Eovaldi has 2 different types of pitches that he sequences, and both of them he tunnels rather frequently and is very successful when he does so. Our next metric is the top 5 for the tunnel strike rate. We can see a new leaderboard here, and this is the amount of strikes that they're getting what percentage strikes they're getting on that second pitch when they are tunneling. So we can see Keegan Atkin at the top with 100% strike percentage. However, he is only tunneling this pitch 5% of the times that he throws it. So 7 out of the 141 combinations he's thrown, only 5% of those have been tunneled. However, when they are, he has 100% strike percentage accuracy. Shifting gears just a little bit, looking at swing timing, which is early versus late. I pulled a great example again of Kevin Gossman, who is pretty known for his fastball and splitter combination. One that I touched on before, he's thrown 518 times and tunnels about 10%. So when he throws this, the average tunnel separation distance between those two pitches is sitting at about 4.5 inches, and he is getting above 50% strike percentage on that second pitch. But we can see when he throws the first pitch of this combination, on average, a batter is 1.7 milliseconds early versus when he throws that second pitch, that batter is 2.9, so almost 3 milliseconds early. So we can see that change in swing timing due to tunneling. Here's a video clip of Gossman throwing 2 tunneled pitches. And we can see them side to side, how close they are together and how they diverge pretty late in the flight. So now looking at some future considerations I had if I had more time to do this analysis, I think one thing that I would look into would be extending the analysis from pitch pairs to full at-bat sequences. So in other words, right now I'm looking at 2 consecutive back-to-back pitches, but I would be interested to see if I could expand this to maybe looking at the first and third pitches in a sequence, or maybe the fourth, fifth, and eighth pitch. Just seeing how often within that at bat a pitcher is tunneling. Additionally, I could look into replacing league average commit points with a more adaptive sequence-specific measurement with using that biomechanical data. I did pull an average with that 167 milliseconds since plate, but I think if I really wanted to get more precise, we could do it on a per basis, per batter situation. Following that, I'm curious to see if the pitch tempo affects the tunneling at all. That is, how quickly versus how long a pitcher might wait before throwing that next pitch. Are they trying to pick off a runner at first base? Does timing affect that at all? I'm also interested if some pitchers can hold their tunnel for longer. So after those 2 pitches are hitting that commit point, how long are they staying tunneled before ultimately diverging? I'd also love to explore some leaderboards looking at which players have the greatest difference in swing timing, whether that's early or late when they tunnel. So when they are tunneling 2 pitches, how is that affecting batters? And then lastly, I would love to expand pitch tunneling to the batter side and seeing how they perform when 2 tunneled pitches are coming at them, possibly leaderboards on who is the best at hitting against tunneled pitches. Thank you guys for your time. That was all that I had for today. I was really excited to share some of my summer work, and I please encourage you to contact me if you have any questions or comments at my email below. Thanks again.